So let's go on. The rational zeros theorem, we didn't mention that last time. I don't think it's that important, but let's do it as an example of some basic math. Okay, so rational zeros theorem. Rational zeros theorem. Okay, so this one says, remember what we were talking about. One of the proofs that we did last time was to show that the square root of 2 was irrational. Okay. This is another way that one might see that the square root of 2 is irrational. So here's the theorem. Suppose that you have a naught, a1, an that are integers, and you have a polynomial equation a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a1x plus a naught equals 0. Let this be a polynomial equation with n, some natural number n, a sub n is non-zero, and a sub 0 is non-zero. Okay. And the claim is that if P over Q is a solution of this equation, let's call this equation star. If P over Q is a solution of star with P over Q in lowest terms, then Q has to divide a sub n, and P has to divide a naught.
Can you say P and Q are relatively prime?
Yeah. So they're relatively prime, right? Yeah. So there's no common divisors. That's right. Sorry, it's a term that I haven't used in a while. Okay, and so for example, if we're looking at x squared minus 2 equals 0, right? The solutions, if there were rational solutions, any rational solutions of this, right, P over Q, would have to satisfy that Q divides 1 and P divides negative 2. Right? In other words, Q can only be plus or minus 1, and P could be plus or minus 1 or plus or minus 2. Right? Would satisfy this. And so the only possible rational solutions are plus or minus 1 and plus or minus 2, right? Are the only possible rational solutions. Right, and so you see that none of these work, and so the solution of this, it has to be an irrational number. Okay, so this may be I don't know if you saw this when you were in junior high school or elementary school at some point. Anybody see this? No? I remember seeing this in high school, I think. And it was never explained, right? But it actually has an easy explanation. So here's the proof. Okay. Did anybody understand the proof well enough to talk about it? Can anyone tell me how the proof runs? Anybody? No? Okay. So I don't have any sort of intuitive idea for this proof. It's a purely algebraic proof. So here it is. Saying, well, let P over Q be a rational solution of star. In that case, well, A sub n, P over Q to the n, plus A n minus 1, P over Q to the n minus 1, oops, n minus 1, plus dot dot dot, plus A1 P over Q plus A naught is equal to 0. Okay. Then multiply the whole thing through by Q to the n. So you get A n P to the n plus A n minus 1 P to the n minus 1 Q plus A1 P Q to the n minus 1 plus A naught Q to the n equals 0. Okay, so just multiply by Q to the n. Multiply through by Q to the n. Okay, and then what you see is that A n P to the n equals something that I can factor Q out of, right? Q times, negative Q times A sub n minus 1 P to the n minus 1 plus dot 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 A1 P Q to the n minus 2 plus A naught Q to the n minus 1. Okay, so move all this stuff in the parentheses over to the other side. Okay. Okay, and so what you see is that Q has to divide A sub n times, Q divides both sides, right? Q divides the right side, but the right side is the same as the left side, right? So Q divides A sub n P to the n, okay, but P and Q have no common factors, so Q must divide A sub n. Okay, and I should say that the book is cheating you a lot with this arrow, and they sort of indicate that. They say, oh, actually, we need to involve unique factorization. So there's a lot of this step is actually far from justified. Okay, but the book is just going to leave it at that, and I think we should too, rather than talk about unique factorization. Okay. But in any case, let me just say that this then actually requires more justification. Okay, and then similarly, you move everything involving the p's to the other side. You factor out a p, right, and you see that that p has to divide a naught q to the n, but that implies that p divides a naught. Okay, so that's the algebraic trick, and again, it involves something called unique factorization. Yeah, that you can take a number and there's a unique factorization of integers into primes. Yeah, Aria.
I guess I don't know if this is part of what you're talking about, where you're talking about the book cheats us.
Yeah.
But I'm kind of confused why P and Q can have no common. I don't know what the word is. Like things that go into them, because so I understand like if
there were
3
common
halves is rational, that's saying the same as like 6/4.
Yeah.
But then 6/4 is still rational, right?
Yeah, but so what they're saying basically is that you put it in lowest terms, right? So you divide out if there are any, if there are any common factors, you cancel them out. Okay, so start off with your 6/4, right? Start off with your 6/4, but you've got your root. You've got your root. Express it in lowest terms. Whoops, I canceled the wrong thing. Sorry. express it in lowest terms, right? And then start this proof.
Okay, so when we have just like P and Q, then we're assuming that they have no common things, because
Right.
you could have canceled anything that was common.
That's right. That's
Okay.
right. And in some sense, actually, that also is assuming some sort of factorization. So unique factorization. So yeah. So there's more cheating involved. Yeah. But anyway, just to give you the idea. Okay. So yeah. Okay. Okay. In any case, this is not at all. It's not that important. Okay. Okay. So let's go on to section 3. Section 3: field axioms and distance. Okay. So. Okay, so the way you want to think about this is that we're going to take things that are familiar, like the rational numbers, the real numbers, and we're going to sort of abstractify them. Okay, we're going to look at them and we're going to say, what kind of properties do these both have? Okay, these are examples of something called a field. Okay, we'll try and write down, some qualities of these things. Okay, so if we consider the real numbers, say, okay, well, the real numbers have an addition. They also have a multiplication, right? Okay, so we consider the reals, but not just the reals. We consider the reals with these two binary operations on it. Okay, we notice that there's a bunch of things that are satisfied. One that you have an associative property, right? You have an associative property for addition, right? A plus B plus C equals A plus B plus C, right? Where A, B, and C are real numbers. Whoops. Are real numbers, right? You have a commutative property, right? A plus B is B plus A, right? You have an identity element. There's something that you can add on. There's something that you can add on, so this is called the additive identity, right? There's something that you can add on and it doesn't do anything, right? And then there are what are called additive inverses, right? For each A, there exists some sort of negative A, such that A plus negative A is the additive identity. Right? So we notice that the addition satisfies certain properties, right? And we notice that the multiplication also satisfies analogous properties, right? Right? Multiplication is associative, it's commutative. There's a multiplicative identity, right? The number 1, right? When you multiply by 1, nothing happens. And there are multiplicative inverses, although not for 0, right? So there's multiplicative inverses. If A is not equal to 0, then there exists some sort of A inverse in R, such that A times A inverse equals the multiplicative identity. Okay. So the addition satisfies certain rules, the multiplication satisfies certain rules, and they satisfy together. The way they interact satisfies the distributive property. Okay. So, if you look at the real numbers, or if you look at the rational numbers, right? If you look at the real numbers or the rational numbers, you see that they both satisfy this list of properties, Okay, so we take that as a general definition, as an abstract definition. We say, so these things all, so these, the above, although I guess they're below right now, are called the field axioms. Field axioms, right? And any triplet set with an addition and a multiplication satisfying them is called a field. Okay, and I think there should be some rule here that where f has more than one element. Okay, so it is possible to create a field with one element, but we're not going to. That we'll consider it as a degenerate case. Yeah, Aria.
Is always going to be addition and multiplication.
Yeah, yeah, but it may not be the addition and multiplication that you're familiar with, right? So as long as there's some set, and there's some way of adding elements of this set that satisfies this, and there's some way of multiplying elements of that set that satisfies this, and the two interact well in this sense, then we call them a field. Call that thing a field. So the addition might not be the addition that you're familiar with. The multiplication might not be the multiplication you're dealing with. You're familiar with. Okay. So right. So for example, if we look at complex numbers, right? They have an addition. They have a multiplication. Right, that turns out to be a field. If you look at the integers, are the integers a field? No, why not, Nick?
Because you can't do multiplication. There's no inverse for multiplication.
Right, there's no inverse for multiplication. Right, you can't get back to 1. Right, so if I start from 2 and I say multiply by something and get me back to 1, there is no multiplicative inverse for 2. Right. Okay. What if we look at Z mod 3 with the regular addition and multiplication? Z mod 3, right? Is that a field? Right, so your elements are 0, 1, 2, right? Where, if you go beyond 2, you circle back, right? So 2 plus 1 is 0. 2 plus 2 is 1. You see what I mean? Right, so it's like a clock, right? 0, 1, 2, right? 2 plus 2 is 1. 1 plus 2 is 0. Right? Okay. Z mod please. Right? 2 times 2 is 1. Right? 1 times 1 is 1. Right? So for the non-zero elements, I actually do have multiplicative inverses. Right? 2 times 2 is 1. 1 times 1 is 1. Right? So I can get back to 1. It does have multiplicative inverses, does have additive inverses, it has everything. In fact, so this actually is a field. Yeah,
What did the C right there stand for again?
complex numbers.
Complex numbers.
Complex.
They are closed under addition and multiplication.
Yeah, if you don't like them, just we're not going to talk about them at all in this class. So, yeah. Okay. Okay. So here's some examples. What about Z mod 4? Anybody have an idea about that? Z mod 4, is that a field? The answer is no. Okay, and we'll see why that's true in a second. So here are some basic properties of the real numbers, right? But the real numbers actually have a lot of other properties. You notice that we didn't include, some basic things like anything times 0 is 0, right? Or this sort of stuff. So why didn't we include them? Well, because they're all actually consequences of these. We don't need to include them. They're all consequences, the important ones. So with this theorem, let F be a field, then for any A and B in F, the following are true. So we have a cancellation. If A plus C equals B plus C, then A equals B. Right? You can cancel. A times 0 is 0. Property 3, the additive inverse times B is the same thing as the additive inverse of AB. Number 4, the additive inverse of A times the additive inverse of B turns out to be AB. Number 5, if AC equals BC and C is non-zero, then A and B must be the same. So you've got cancellation. This is again cancellation, but for multiplication. And 6, if AB equals 0, then A equals 0 or B equals 0. Okay. In other words, there's no way to multiply two non-zero elements and get 0. Right? If you multiply two things and get 0, one of them had to be 0. Right? There had to, right? One of them had to be 0. Okay. And this maybe tells you, at least give you some indication why Z mod 4 is not a field. Right? Because you can get to 0 by multiplying 2 times 2. Right? 2 times 2 is 0. Well, that's not supposed to happen in a field. Right? In a field should be whenever you get 0, whenever a product is 0, one of the factors must be 0. Okay, so all of these things we don't need to include in the axioms because they are consequences of the axioms. They are not particularly exciting consequences, and their proofs are not particularly exciting either. Let me give you some examples. So the first one, showing that we can cancel. Right? So say that A plus C equals B plus C. Okay. Well, in that case, A plus C plus negative C equals B plus C plus negative C. Right? Right. We add negative C to the same thing. Right? This is equal to that. We add negative C to it. Okay. Right. But then by associativity, right? Right. So this is by associative property. Right. But then this is A plus 0 equals B plus 0 by the definition of additive inverse. Right. But then A equals B because of the 0 is the additive identity. So cancellation is okay. Okay, and you see that we needed to use various properties to do it. Okay. Okay. So if you I think in the homework you might be asked to prove some things along these lines. You see that you have to invoke the field axioms to do it. One of my ex-students went to a math camp when she was in high school, and she said that they started off by with the field axioms and then proving basic things using the field axioms. That seems to me like the worst way to to introduce math. But it's true. You know, you start with some basic axioms and then prove some simple things using them. Maybe that's one way to do it. But it seems to me that would kind of kill people's enthusiasm. Anyway, so let's do number 2. I guess we'll stop there. Okay, so why is it true that a times 0 is equal to 0? You say, well, so we want to show a times 0 is equal to 0 for anything. So, okay, well, a times 0 is the same thing as a times 0 plus 0 because of the properties of the additive identity. 0 is the same thing as 0 times 0. That's the same thing as a times 0 plus a times 0, right? By the distributive property. If I add 0 to the left side, nothing changes. Again, so additive identity. Right? But then I use part 1, cancellation, shows me that 0 equals a dot 0. So I cancel off the a times 0 from both sides. Right? And that shows me that a times 0 has to be equal to 0. Okay. So what's the point? The point is that, other than that this is not interesting, the point is that there are these things called fields, and they satisfy certain axioms. The axioms imply sort of basic properties that you would expect. So don't be confused. There are all sorts of fields. Okay, like you're comfortable, you're familiar with your real numbers and your rational numbers. But if we're talking about a general field, you can't assume that we are one of those fields, right? It could be something very abstract. Okay, so all you know is those basic axioms. Okay, and thankfully those basic axioms imply certain things that you would like to have. Okay, that's it for today.